Hello there, this is the third video for polynomials. This is one of my favorite topics just because it's a mystery to try to figure out what these zeros of these polynomials are. And as we go along, we'll certainly get plenty of practice in class. And there are lots of ways that you could actually figure out the zeros for polynomials, and we're going to cover a few of them. I'll have some big comprehensive examples for you as we go along. So we've got examples here, but I'm going to introduce a couple of major theorems and ideas that will help us to factor our polynomials really quickly. The first one is this is called the fundamental theorem of algebra. And it basically says a polynomial function of positive degree n has at least one zero in the complex number system. Now, one thing that's the corollary of this that'll be really important going forward, and we kind of already have an idea of, is that a polynomial function of degree n has exactly n zeros. So that includes repeated zeros. So like if x equals 2 was a root that had a multiplicity of 2, we would count 2 twice. And then this is in the complex number system. So if we have x squared plus 1 as a factor, then we might end up with what we call imaginary roots. So remember that I squared is equal to -1, or the square root of -1 is equal to I. This is what we call our imaginary unit. All right, and so this will be what allows us to come up with all of our roots for our polynomial. A complex number, by the way, is a number of the form a plus bi. And as we'll see, because of the way that complex zeros come about, that's through the quadratic formula, we'll see them occur in what we call conjugate pairs. So if a plus bi is a root, then a minus bi is a root. So if 3 plus 4i is a root, 3 minus 4i has to also be a root. We have three ways that'll make our synthetic division go faster, as we saw in the previous video. And so we might have a whole possibility, the big possibility of roots, but we can narrow them down with a few ideas here. The first is what's called the rational root theorem. And in short, all rational zeros are the form p divided by q, where p is a plus or minus factor of our constant, and q is a plus or minus factor of what we call our leading coefficient. And I'll show you an example of that in just a minute. We also have what's called the upper bound and a lower bound test. And the idea is that if you test a negative number in your synthetic division, and your last line of your synthetic division all has non-negative or non-positive numbers, and they alternate, then we say it's called a lower bound. So it's the lowest possible value you could ever have. If you test a positive C and the last line is all non-negative numbers, right, meaning all positive numbers that are not, or zero, then C is an upper bound. We also have what's called Descartes' rule of signs. And it basically says that our maximum number of positive roots is the number of sign changes we see in the polynomial coefficients. And then the maximum number of negative roots is the change of sign of the odd powers. All right, and then we check the number of sign changes. So it seems like a lot right now, but basically these are all like kind of hidden tricks that you can see in a polynomial that'll help make this synthetic division go faster. So let's do an example here. First, we want to analyze and then graph x to the fourth plus 2x cubed minus 7x squared minus 8x plus 12. All right, so first of all, this looks like a really complicated polynomial. It's an x to the fourth. How in the world do you figure out which roots to try, which zeros to try in your synthetic division? So our first tool to help us out is what's called our rational root theorem. And what it tells us is that our possible rational roots are only going to be the plus or minus factors of our constant divided by any plus or minus factors we have of a leading coefficient. So I made this first one easy. We only have our 12 here as our constant and a 1 as our leading coefficient. So our possible rational roots in this case are just the plus or minus factors of 12. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. All right, those are our possible rational roots. Upper and lower bounds. So here's the idea. What we can do is we can test some of these values that we got. Usually it's good to test values that are kind of in the middle. And if we see things that happen with our synthetic division in these roots that we're testing, then we can either claim that we have a lower bound or an upper bound. So for example, I'm going to assume, by the way, that we know how to do synthetic division. So I'll show you what's going on, and then I'll explain what's happening, but I won't go through all the details of the synthetic division. If I try -4, for example, right here, you'll notice what happens in our bottom row here. When I did synthetic division, I get the signs to alternate positive to negative, positive to negative, positive to negative. If you see the signs alternate when you plug in a negative number, that number is what we call a lower bound. So -4 is a lower bound. That means we don't need to test -6 or -12, and in fact don't need to test -4 because we didn't get 0 here. right? So any negative roots are going to be -1, -2, or -3. So you see how right away we were able to eliminate a whole bunch of roots. If, on the other hand, we try something in the middle like 4, all right, and you can see my lovely sloppy synthetic division here, you notice that in my bottom row, I get my signs to all be non-negative. They're all positive numbers. So that means that 4 is an upper bound when I plugged in a positive number. So again, we don't need to test 6 and 12 or 4. All right, so the only things we need to test are numbers between 1, 2, and 3 and their negative versions. Finally, we have what we call Descartes' rule of signs. This is another nice little hidden trick that you can use to quickly solve a polynomial. So the way it works is you want to check to see where you see sign changes in between your coefficients. So as you can see, we went from a coefficient of 1, x to the fourth, to 2x cubed, no sign change there, to a negative 7x squared. So there's a sign change between a positive 2 and a negative 7. Then we went to a -7, from a -7 to a -8, no sign change, but then -8 to 12, right? So in this case, we see 2 changes of signs from positive to negative or vice versa, right? So 2 sign changes mean we have 2 maximum positive roots. Now what happens since the roots become in pairs, all right, we can't have one positive root, but we can go down by 2s basically to get the next possibilities. So here we could have 2 positive roots as our maximum, or we could also have 0 positive roots because we can subtract some sort of a multiple of 2 to get our next set. With negative roots, what we're going to do is we're going to change all of the signs of our odd powers. So you notice I changed the sign on the 2x cubed, and I changed the sign of 8x. And now when I check it, I got a sign change between x to the fourth and -2x cubed, between -7x squared and 8x, and no other sign changes there. So 2 sign changes again means my max number of negative roots is 2. And they again go down in pairs. All right, so we could also have 0 negative roots. How is this helpful? Well, what roots should we test? Only those 6 are the ones that make sense to test. -3, -2, -1, 1, 2, and 3. All right, and then we just do synthetic division. So I did synthetic division on -3 and got a 0. I did synthetic division on -2, also got a 0. And on 2, I got a 0. And then I ended up with also x minus 1 is my final depressed polynomial. And so I have 4 zeros, -3, -2, 1, and 2. All right, and I know I just kind of sped through that process. It takes a little longer sometimes to do that. All right, but there's the idea that we're going to do synthetic division to actually find those zeros. All right, so let's try another one here. Analyze and then graph f of x equals 3x cubed minus 8x squared minus 5x plus 6. All right, so again, we want to list our possible rational roots. Those were our factors of our constant divided by our factors of our leading coefficient. So factors of our constant include 1, 2, 3, and 6, and we put plus or minus there. And then we can divide all those by factors of 3. So 1, of course, is a factor of 3. We already did that one. But then we divide by 3. 3 is a factor of 3. So we take all of our roots right here, and we get plus or minus 1/3, plus or minus 2/3, plus or minus 3/3, and plus or minus 6/3. So notice that 2 of those are repeats, okay? But I wanted to list them all out so we can see what's going on. Upper and lower bounds. So one thing that I can test is -3. That's kind of somewhere right in the middle. And when I test it, I notice that my signs change. There should be a -132 here. So I went from positive to negative to positive to negative. So -3 is a lower bound. All right, and then I can test 4. There's another example here. That's not one of our possible roots, but it does give us an idea that all the signs at 4 are non-negative. So we have 4 as an upper bound. So that means 6 doesn't make any sense. Neither does -6 or -3. Then we can look at Descartes' rule of signs, our positive roots. All right, we go from 1 sign change from 3 to -8, and another sign change from -5 to 6. So that means we have 2 or possibly 0 positive roots. If we change our signs on our odd powers, all right, we can test our negative roots, and we end up with 1 sign change, and that means we have to have a negative root. So all this is telling us something. We know there are some rational roots that don't make any sense. We know that there has to be 1 negative root. So what do you think I should test first? Well, how about we test a negative root? And as I go through here, you notice that I do test -1. I also test 2/3. All right, and so when I go through and test my synthetic division, I get 2/3 and I get -1. and then I end up with a 3x minus 9, which gives me another root of 3. And as you can see, all right, the end behavior of this is an odd positive polynomial, and we go through each of our roots. All right, analyze and then graph our final one here, x to the 4th plus 4x cubed plus 5x squared plus 4x plus 4. All right, rational roots are all factors of our constant here, plus or minus 1, plus or minus 2, and plus or minus 4. Upper and lower bounds, all right, the signs don't alternate here. So the lower bound has to be somewhere beyond -4, so it doesn't actually help us here. All right, we get some positive and some negative. However, if we test 1 as our root, we see that we get nothing but positives here. So that means 1 is an upper bound. All right, that tells you something. That tells you that basically we need to just be looking at our negative roots when we do this. And the Descartes rule of signs actually helps us see that. If you notice, we had no sign changes with our positive roots. So none of them are positive. That makes sense because 1 is our upper bound. But when I change my signs, all right, I notice that I get 4 sign changes, a whole lot of them. So that means we could have 4, 2, or 0 negative roots. So what do you think we should test? Nothing but negatives. All right, and that leaves us with -1, -2, and -4. So when I do synthetic division, I tried it on -2, right? And I ended up with this lovely depressed polynomial. All right, you could try -1, -4. Sometimes it happens that you might need to try a root again, as we do right here. And when I try -2, I find that we had -2 as a root twice. All right, the multiplicity was 2 on that. So here we're left with x squared plus 1 as our depressed polynomial. So what zeros does that get? Well, we're going to talk more about this in class, but basically when we set x squared plus 1 equal to 0 and solve, we get x squared is equal to -1. And as I said before, the square root of -1 we call I. So these are our 2 complex roots here. So we do have 4 roots altogether, -2, -2 again, and then I and -I. It just so happens that 2 of those aren't real roots. All right, and so here's what the graph of that looks like. We got our roots at -2, -2, -I, and I. And at -2, of course, since that root happens twice, we bounce off the axis. And as you can notice, this has an even positive end behavior. All right, so we get this weird, funky looking graph like this. All right, so in summary, lots of things can help us find zeros for a polynomial. We got our rational root test, very helpful for eliminating a lot of possibilities. Upper and lower bounds help give us a range of values that make sense for us to test. And then Descartes' rule of signs helps to tell us the number of possible positive or negative roots, which also helps us to figure out, well, maybe we don't need to do any positive guesses like in the previous example. All right, watch out for those complex roots. We'll talk more about those in our next class. So thank you for listening, and we'll see you in class.